Greetings, everyone. Welcome to the 18th International Conference on Artificial Intelligence and Law, hosted by University of São Paulo. My name is Rafael Saravalli, and I'm going to open the floor of the first panel of the fourth day of the event. But before that, in the name of the ICAI organization, I'd like to thank our platinum sponsors, Jus Brazil and Albert Einstein Israeli Hospital, our gold sponsors Logarithm, Legal Code, and PG Lawyers, and our silver sponsors Urbano Vitalino Lawyers, Opsi Bloom Lawyers, and Oasis Open. Now, I'd like to introduce you Mr. Lukasz Gorski, who will present and answer the paper with the title Explaining Artificial Intelligence, Lawyer's Perspective. Mr. Lukasz Gorski, you have 20 minutes for speech. Afterwards, we'll move on to the questions. The stage is yours.
Thank you. Just let me share the slides. I hope that the presentation is visible now. And let me begin. Explainability has always been at the heart of artificial intelligence and law curriculum. The growing popularity of deep learning methods makes inquiry into deep learning explainability even more important. Moreover, it is of value not only in artificial intelligence and law, but also in general artificial intelligence research. In this work, we aim to quantify and test the usefulness of different explainability methods when applied to the area of legal text classification. Those methods were evaluated using the opinions coming from the legal professionals. This work was performed by Sashika Ramakrishna from Free University Berlin, as well as by me, and I am currently employed at the Interdisciplinary Center for Mathematical and Computational Modeling at the University of Warsaw. This talk will be structured as follows. Firstly, I will start the presentation by stating the research question, and I will also refer to our previous work to fully present the motivation before the research undertaken here. Secondly, I will talk about the computer system we have designed and implemented for our experimental explanation generation. The discussion of systems architecture will be supplemented by the review of dataset that was used. Finally, I will describe the results of the pilot study that we conducted based on the explanations generated by our system. So to begin, when the motivation is concerned, it should be noted that this work is a significant extension of our previous paper presented at the Xyla workshop during the previous Jurix conference, with extended version accepted into ICOL proceedings. In this aforementioned paper, we have presented a classification system that was based on convolutional neural network, and that system used GradCam method to highlight the most important words when doing the legal text classification. However, the choice of GradCam as an explanation method was somewhat arbitrary. And in the work presented here, we explored different methods of explanation generation for convolutional neural networks. Thus, with the work presented here, we aim to give a more structured and rigorous means of assessing different existing explainability methods. In general, there are three main categories of methods that can be employed for convolutional neural network-based explanation generation. Firstly, already mentioned GradCam is commonly used in computer vision. It uses the gradients of the target concept that flow into the final convolutional layer, and it produces a coarse localization maps that highlight the most important regions in input data that were the most important for predicting the concept. The second method that is presented here is SHAP. It is a game theoretic approach that aims to explain the output of any machine learning model, and it generates explanations using the Shapley values from game theory and their related extension. And thirdly, LIME is an example of surrogate model-based diagnostic, and it builds a local interpretable model based on the perturbation of input data fed to the model. Thus, to sum up, in our research, we wanted to uncover what lawyers think of explainable artificial intelligence systems and of the methods that can be used in those systems. The tag cloud presented on this slide comes from the survey we have circulated among legal professionals, where we asked them about their views on what features they would desire from explainable artificial intelligence-based system. Generally, they talked mainly about tools that will take the burden of manual work away from the lawyer. Many people mentioned a transparent decision process, but as will be shown later in my talk, the conceptualization of transparency varied in the opinions given by various respondents. Another thing that may be noted is that when we ask about explainable artificial intelligence, many respondents were talking about general artificial intelligence system. Thus, they were viewing those two terms as, in a way, synonymous. And in conclusion, we may say that explainability for a lawyer is a crucial feature of the system, and it is indispensable in their mind, and it is a necessary element of any artificial intelligence-based system for law that can be used by the lawyers. Moving on to the methodology, we have built a modular system. In its heart, it has a convolutional neural network, like here. The implementation of the networks that we have used was sourced from an external authors and used with their permission. We have used the system developed by Hebin Shin, which was based on theoretical insights from Yoon Kim. Our core contributions to the system is the extension of the embedding module to support various embeddings, like what2vec or BERT. Secondly, we have introduced artificial intelligence and law-based datasets to the system. And thirdly, we have added pre-processing tools as well as a metric comparison module. This metric comparison module is based on the insights from computer vision and uses a well-known set of metrics to generate insights into how the system works. In the experiments that we present here, the convolutional network was trained on the PTSD dataset. For testing purposes, we allow a user to choose a variety of embeddings. However, in this research, we have settled down on using distribute-based embeddings. Though other versions of the systems I have already set allow to choose another set of embeddings. The part that will be crucial in this presentation is the fact that the CNN module was coupled with the visualization module, which generates heat map that show the most important words that impact the classification of the convolutional network. For this paper, we have explored how can the visualization module be extended to accommodate different kinds of explanation generation methods. In addition to GradCam, which came out of the box in the CNN implementation that we have sourced, we have coded a sharp and line explanation generation module. In the remainder of this presentation, we will focus on those additions and how they were assessed by the evaluation group that consisted of professional lawyers. As for the dataset used, as already mentioned, we have settled down on using the well-known PTSD dataset. It is a collection of 50 judgments coming from the US Board of Veteran Appeals. Each sentence of those judgments was annotated by human annotators according to the rhetorical role that those sentences play in the judgments. There were 6 roles distinguished, and the exemplary sentences are shown at the bottom of the slide. Our convolutional network was trained on this set, and we achieved relatively good accuracy of about 83%. Though we really did not focus on the efficiency of the classification task, as our main aim was user-based evaluation. Nevertheless, we conclude that those results in terms of accuracy are already satisfactory, and we believe that they can be improved down the line when more work is put in this area. The most important part for this presentation was the fact that the network was used to generate explanations in the form of heat maps, as presented here on the slide. Each explanation method generated a distinctive set of heat maps. We have chosen 6 sentences from the PTSD test set that were correctly classified by the network, and explanations were generated for each of those sentence types. Like 3 explanations were generated, each for GradCam, Sharp, and Lime. To assess the usefulness of those explanations, we have prepared a survey which was circulated among legal professionals. They were instructed that the computer mark the parts of the sentences which were the most decisive for making a decision regarding the classification. The lawyers were then subsequently asked to grade each of the explanations on a scale 0 to 10, with 0 being worst and 10 being the best. The slide that is presented now presents an overview of the results for a sample sentence. Next to the sentence's heat map, we present the average user score, as well as the resulting, and we have also assessed the explanations in terms of the metric that comes from a computer vision. In the paper, we give a set of 2 metrics. Here, for this slide, we show the metric which in full is called fraction of elements of relative threshold, and this metric represents what portion of input data was taken into account by the CNN. It can be clearly seen that Sharp highlighted the whole sentence, while GradCam was the most selective method. So there were differences in our respondents' assessment of various methods. Statistical analysis shows that those differences were not statistically important. Therefore, it can be said that all the methods were assessed by our respondents similarly. And when deciding what method to use in a computer system, other factors should be taken into account. For example, from a software engineering point of view, it should be noted that implementation of certain method is dependent not only on user's voice, but also on technical feasibility. GradCam is a method that, to the best of our knowledge, works only with convolutional networks. Lime is a method that is dependent on a number of hyperparameter values, and there are papers that suggest that it can be tweaked to the point of showing anything that the programmer wants. As well as the technical merit is concerned, we have used open source libraries for implementation of different methods and have found that the quality of implementation is varying. Thus, this may also be a factor that can be taken into account. And finally, let me make some additional remarks. Let's return to the example that was shown on the previous slide. Here, it can be spotted the results between different explainable artificial intelligence methods vary widely. For example, when I have seen the results coming from Sharp, my first comment was that it has gone ballistic. Yet, there was a disagreement between the respondents, and 8 of them said that the results for the citation sentence given by the Sharp were the best, while 9 experts have graded it as the worst. Thus, there seemed to be an implicit disagreement between different respondents as what exactly is the best explanation. This can be further strengthened by different comments that we have received from the respondents after performing the survey. For example, one of the respondents has said that he did not do this part of the survey at all because he was confused by what those colorful words were supposed to mean. On the other hand, the other expert has said that it made him question how he thinks as a lawyer, because this classification task is something that he would do intuitively. He had implicit mental model of the task, and our survey made he question how that implicit mental model really works. In addition to the part that I have already shown, the lawyers were also asked a number of generic questions regarding their stance towards the artificial intelligence in general, as well as its usefulness in their professional life. This part was meant to elicit the requirements for such systems as provided by the respective users. The prospective users, the legal experts, were asked generic questions regarding artificial intelligence and explainable artificial intelligence, and we have also allowed them to freely write what they expect from AI-based systems in terms of justification. As far as the results go, we have in general found the lawyers to be enthusiastic towards the use of artificial intelligence in law. The tech cloud, which was already presented in one of the previous slides, showed the phrases that occurred in the answer most often. Artificial intelligence and law curriculum seems to have penetrated the ranks of the lawyers, as 90% of the respondents see them as useful. Remaining 10% had no opinion, and they were not negative towards the AI-based system. 62% of the respondents have acknowledged that they were already acquainted with the term explainable artificial intelligence. And 52% of the respondents believe that one has to understand the inner workings of the explainable system to receive meaningful explanation, which suggests that understandable explanation that do not that allow one to understand the system's decision without knowing its inner workings is something that needs to be worked on. This concludes my presentation. We consider that the work presented here can be a basis for deeper studies. We had 21 respondents, and obviously future work should include a larger user base. Explanations can be tested using different datasets and other visualization methods, and a more in-depth studies of lawyers' conceptualization of explanation should also be conducted. Most importantly, we think that means of introducing domain knowledge to the explanation should also be explored. Thank you for your attention.
Thank you, Lucas. And now we have a few questions from the audience. The first one, course stacking. The author of asks this. The authors of SHAP show in their NIPS paper that LIME is basically a subset of SHAP without the guarantee of accuracy and consistency. The only advantage that I know of is that LIME is sometimes faster. So why use both SHAP and LIME in your explanation model?
Yes, I agree that LIME can be thought as a subset of SHAP in a way that both of them are based on generating local explainable models. In my opinion, for the full overview, both of those methods should nevertheless be compared. I mean, if there is a method that is commonly used, and to my knowledge, LIME is such a method, that I think that omitting it would be an omission in this paper. I don't know, would Sashi like to comment on this question as well?
No, I think you pointed it right, Lucas. So because LIME is also one of the commonly used methods, right? So we did not want to leave out of the comparison chat that we had, and we did understand that LIME and there's not greater difference between LIME and SHAP. They both originate from a similar principle.
Okay, so we can move on to second question from Trevor Bench Kaplan. All words highlighted got a score of nearly 5 to 10. This suggests that the users were rather undermining. Would no words highlighted also get 5 to 10? And I think the third question will be easy. And from Sabine Weinhardt, how large was the pilot?
I think I should have mentioned that in the conclusion, it was 21 respondents. Yes. And as far as the second question go, the scores of about 5 out of 10 that I have shown on the slides were the averages that we have received. And we have found that the users, when concrete answers by concrete users were explored, they were much more divided regarding their assessment. So the people tended to give high score to certain methods in certain explanations and low scores to other ones. So that 5 out of 10 is just an effect of averaging that was presented here in the results. Thus, based on the individual answers, I can speculate that no what's highlighted would be graded as zeros by the respondents. But this kind of control sample might be good to be added in future studies to see whether they really give it a score of 0.
So I have another question here. Is it possible to notice that lawyers who are not used to the concept of XAI and participate in the survey got more enthusiastic or somehow disappointed with AI in your point of view? Which were their expectations when hear about AI?
The answers that we got, I can make the conclusion based on the answers that we got, and the answers we got were generally that they were enthusiastic towards the artificial intelligence, and 90% of them has shown that that they see the use of such systems. And many of the lawyers have also said that they were knowledgeable of the term explainable artificial intelligence. And I must personally say that I was a little surprised with the results. In general, as I have already said, they were enthusiastic towards the artificial intelligence and have seen this as a method that will take away the burden of manual work from them. But I think that this is something that every professional group may expect from artificial intelligence.
Okay, and I have another question from Trevor. How can every word highlighted explain anything?
I completely agree with that comment. As I have said, when I have seen the explanation given by Sharp, my conclusion was that it is useless. Nevertheless, many of the lawyers have highlighted this as the most important. I think that this shows how the concept of transparency and explanation differs between different particular lawyers. So a more detailed inquiry should be made. To test what do lawyers really want from such an explanation. My hypothesis was that in case of the explanation that marked all the words, the 8 lawyers that said that it was the best explanation wanted the most complete set of words from a given sentence. Like for the citation amounted not only to the reference to a judgment that was cited there, but also the summary of the points that were coming from the judgments. and maybe for those lawyers only that offered a complete explanation of what the system did. At least that's my hypothesis, and as I have already said, this deserves further inquiry.
And another question from Malte Ostendorf. Did you see any difference how useful the explanations were given, a correct wrong prediction from the model?
The short answer is no, and the longer answer would be that we did not test that. When we presented the explanations to the lawyers, we took only the ones that were correct, because we thought that the incorrect ones may be somehow confusing to the lawyers, and this is something that might be explored in the future work.
I have one last question. I have one last question here. Trevor, did you ask any of the respondents about what they like in the explanations?
That was not a part of our survey. The only part that allowed them to get a free input from them was the one regarding what they expect in general from explainable artificial intelligence system. I did talk with some of the respondents after they performed the survey, and as I have already said, one of the responses I got off the record was that it was an interesting exercise in analytic philosophy, because it made him really think deeply how he thinks as a lawyer.
So I think we don't have any more questions. That is no further question here. And I want to thank you, Lucas, for the great presentation and the answers. So unfortunately, now we have to move on to the next presentation. And I think Malte is already here. So now I'd like to introduce you Mr. Malte Ostendorf, who will present the second paper of this panel with the title Evaluating Document Representation for the Content-Based Legal Literature Recommendation. Mr. Malte Ostendorf will have 20 minutes of speech. Afterwards, we will move on to the questions. The floor is yours.
Yeah, thank you for the introduction. My name is Malte Ostendorf, and I'm presenting our paper, Evaluating Document Representations for Content-Based Legal Literature Recommendations. And this is a joint work with Elliot Ash, Terry Ruers, Bela Gibb, Julian Moreno-Schneider, and Georg Rehm. In this research, we explore how state-of-the-art document representation techniques perform in the context of a legal document recommender system. So why did we conduct this research? Literature recommender systems help legal professionals to find relevant literature, and they are getting more and more important as more and more literature is getting available. And in the recent year, there have been much progress in the technologies that underpin recommender systems, mostly based on deep learning approaches like transformer models or graph embeddings. So the question is whether these improvements are also beneficial in the context of a legal recommender system. Besides the technical aspect, we conduct this research also with reproducibility in mind. In general, recommender system research is known to have a reproducibility issue. And this issue also exists for legal recommender systems, where evaluations are often based on a small-scale user study, and also the evaluation data is rarely published. And this leads to inconsistent research results and makes it very difficult to actually reproduce the research. And that's why we set ourselves the following two research objectives. First, we want to evaluate a large variety of state-of-the-art methods. And second, we want to use publicly available data sets so we can make our work reproducible. This brings us to the data sets that we use in our experiments. We have three main criteria for the data set. That is an open license that allows us to share the data without any restrictions. And the data set should be also sufficiently large and also reflect different information needs. The large coverage of the data set is especially important when we want to compare fundamentally different methods like text-based against citation-based methods. We found two resources that fulfill these criteria, namely that is Open Casebooks and Wikisource. Open Casebooks is a platform from the Harvard Law School library where users can create and share open license casebooks. Their corpus consists of around 200 casebooks containing 3,000 cases. And the casebooks cover broad topics, but also rather specific ones. The cases from Open Casebooks are linked to the Case Law Access project. So based on this, we can retrieve full text and also the citation data for all the cases. After some cleaning procedure, we end up with relevance annotations for 1,601 court decisions for this data set. Our second data set is Wikisource. Here we utilize a collection of around 3,000 US Supreme Court decisions from Wikisource. Wikisource is a project like Wikipedia from the Wikimedia Foundations, and they collect original source documents. And this collection we are looking at is a collection of court decisions that is categorized in 67 topics, rather broad topics like antitrust or civil rights. A source for the full text and citations, we map the court decisions to the court listener corpus to have all the data available. And here, as a result, we have relevance annotation for 1,363 court decisions. But how do we derive relevance annotations from these data sets? In our experiments, we are considering a recommender scenario where we have a seed document and we want to know which other document would be a relevant recommendation for the seed. So as ground truth data, we need pairs of documents that are relevant for each other. And the two data sets provide exactly this information. For example, when decision A and B are in the same casebook or in the same wiki source category, we can say that A is relevant for B and vice versa. This relevance definition is, of course, limited. For example, one recommendation still might be relevant despite not being in the same casebook or category. That's why we rather refer to these data sets as silver standards instead of gold standards. However, the advantage is that this approach produces a large number of relevance annotation. For open casebooks, it's 140,000 document pairs, and for Wikisource, it's 200,000 document pairs. And this number is much larger compared to the user studies from related work. And it also enables us to evaluate a large number of methods. In total, we evaluate 41 methods and variations of them, and which 27 are actually presented in the paper. The remaining ones were excluded due to either poor performance or because they didn't provide any additional insights. The methods themselves, we distinguish them in 5 categories. First, we have a IDF baseline. Second, we have word vector-based methods like paragraph vectors or document vectors from averaged word vectors from fast text or GLAF. This is also known as mean pooling of word vectors. And here we test also different variations. One is kind of the original version of GLAF or fast text trained on a generic text corpus. And also one version where we train the word vectors on our legal corpus. We also test variations with an artificial token limit to make these methods comparable to the transformer methods. As transformer methods, we have BERT, Roberter, different sentence transformer models. We have long-former and 2 separately published legal BERT versions. One from Chakaldas et al. From the Athens University of Economics and Business, AUEB, and one from Holzenberger et al. From the Johns Hopkins University, JHU. In addition to the citation text-based methods, we have text-based methods. Oh, sorry. In addition to the text-based methods, we have citation-based methods that utilize the citation graph to derive document embeddings. And lastly, we have hybrid methods that make use of both text and citation features. There is one approach that is the concatenation of document vectors from 2 methods. And also we have the score summation of similarity scores from 2 different methods. And as another hybrid method, we have a sentence transformer model that we train with citations as training signal. Before I dive into the actual results, some more words on our evaluation methodology. We separately evaluate open casebooks and Wikisource. And each of the tested methods here produces document vectors for all documents in the corpus. And then based on the vector representations, we then perform a k-nearest neighbor search to retrieve 5 most similar documents, which are then used as recommendations. For the evaluation, we then compare the seed document and the recommendation candidate with our silver standards to determine whether it is a relevant recommendation or not. As a performance measure, here we have precision, recall, mean reciprocal rank, and our primary metric is mean average precision. Just as a side note, we set K to 5 because of the user interface where we want to deploy our recommender system. We also experimented with different K values, but found the results to be similar. All right, so let's start with the actual results. In this table, we have the tested systems, the dimension of their vector representations, and then the performance matrix for open casebooks and Wikisource. And we have the rank that's based on the average MIP over the 2 data sets. And this is also how the rows are ordered in this table. And also in this presentation, I will now only show parts of the actual table. So please look into our paper for the full version of it. On average, we have the hybrid score summation of fast text legal. So that's the fast text word vectors trained on our corpus, and the citation graph embeddings from point care, and they together have the highest MIP score. But if we view the data set separately, we have a slightly different outcome for open casebooks. It is the text-only method fast text legal that yields the highest MIP. Whereas for Wikisource, it's another hybrid method, the concatenation of fast text legal and Pontcare that yields the highest MAP. The other domain-specific word vectors like paragraph vectors or glove legal are also among the top methods. On the lower end of our table, we have the worst performing methods, which are sentence transformer models like sentence Roberto or the citation method BoostNE. Now, for more insights, let's look at the method categories separately. Here in this table, we see all the word vector-based methods that we evaluated. At the top, again, we have the domain-specific word vectors that utilize the full article text. We see that also limiting the document text to a length that can be processed by the transformers does harm the performance, as we can see here with fast text legal limited to either 4096 tokens or to 512 tokens. The other domain-specific methods like paragraph vectors or glove legal have shown a similar decline when limiting their document length, but are not listed here in the paper. But more important than the token limit is the in-domain pre-training of the underlying word vectors. As we can see here with the original glove and fast text, those kind of generic word vectors were trained on Wikipedia or news text, so nothing was legal. As third category, we have our transformer models. And yeah, despite being very successful for many NLP tasks, one major weakness of transformers is that they are made to process relatively short text. So for example, in BERT, the limit is 512 tokens. In Longformer, it is 4096 tokens. And in our experiments, we have legal documents that are typically longer. So here we only can process the first n tokens of the documents that fit into the corresponding transformer model. And that's, of course, one limitation here of the transformer models. And to make the results comparable, at the top here, we have the legal, fast text legal version, where we have the similar limited token number. And exactly these two fast text legal variations are also on average better than all other transformer models. Whereby for open casebooks, the token limit has a stronger effect on the performance. Here we have Longformer large, the best transformer model, and it also outperforms the 512 token version of fast text legal. For the other data set, for Wikisource, the token limit is less critical. Instead, the in-domain pre-training has a greater effect. So here we have the two legal BERT versions are the best transformer models. And generally, we found that from the two legal BERT versions, the one from AOEB outperforms the one from JHU. And we see this reason for this outcome in a larger and more diverse pre-training corpus that was used from the one from AOEB. Similarly, we see that among all transformer models, the large version outperformed the base version. For example, here, Longformer or BERT. But yeah, overall, the performance of the transformers is relatively low. But one could expect that there might be a performance gain when, for example, you would train a Longformer model on a legal corpora. Yet these potential performance gains will most likely not justify the computational effort, in particular when we already have very simple and yet effective methods like averaging word vectors. And this is also what we found when we analyzed how the performance changes depending on the length of the seed documents. And there we found that even for short documents, fast text legal outperformed all the transformer models. In addition to the text-based approaches, we also evaluate citation graph embeddings. And in this category, we have a SPAT method, point care, closely followed by walklets. And overall here, we found that there's a strong dependency on the availability of citations. And that's why we say, or we suggest that these citation methods are actually better combined with text-based methods. And this is exactly also what our evaluation of the hybrid methods show. Here as hybrid methods, we focus on the combination of the previous best single methods, which are fast text legal and point care. Other combinations like glove and walklets have shown a similar performance, but they are excluded because they didn't provide any additional insights. The best methods in this category are also the best methods overall, and that is the score summation of fast text legal and point care. And again, here we also see a difference between the performance of open casebooks and Wikisource. While for open casebooks, the score summation is the best hybrid methods. For Wikisource, it is the concatenation of fast text legal and point care. Other combinations, especially the one from two text-based methods, like here fast text legal with long former, do not lead to the same performance gains as the combination of text and citation-based methods. And why the combination of text and citation improved the results is clear when we now have a look at the similarity of the recommendation sets. In this heat map, you can see the Jacquard similarity of the recommendations of two methods, where Jacquard similarity of 1 means that all recommendations are identical, and 0 means no overlapping recommendations. And what you can see here is a higher similarity between the text-based methods and also between the citation-based methods. But when you compare the similarity between text or word vector methods and citation methods, the similarity is low. So this means that they produce a different kind of recommendations. And this is also why combining them in a hybrid manner leads to this performance improvement. All right, so what conclusions can we draw from our experiments? First of all, document vectors from averaged word vectors achieved surprisingly the best results for all single methods. In particular, fast text word vectors trained on our legal corpus performed the best on both data sets. The training of such word vectors does also not require any special hardware like GPUs. And even when we introduced this artificial token limit, the performance of fast text legal was still comparable high. On the contrary, we have the performance from the transformer model that were rather disappointing. Of course, we have the weakness of the token limit, which is especially a problem when we have lengthy documents like these court decisions. And of course, there are promising research efforts like the long former that are capable of processing more tokens. However, right now, training such a model and especially applying it in a production environment requires much more compute resources. And these potential performance gains do not really justify these efforts. Much less effort actually does it take to combine text and citation methods in a hybrid manner. In our experiments, we use very simple approaches like the concatenation of vectors or just adding up similarity scores, and still outperformed all other single methods. Lastly, we also validated our quantitative findings based on the two silver standards with a domain expert who agreed in 70% with our silver standards. And this high agreement and also the large quantity of the two data sets makes them very interesting for future work, where we plan to use them to benchmark also new different document representation methods. All right. Yeah, thank you very much. Please feel welcome to look at our code and dataset. It's all available on GitHub. Yeah, thank you very much.
Thank you, Malte. And now I have some comments and questions here. I'm going to read for you, okay?
Sure.
First, from Sabine Wenhart. I just have a comment that I don't agree with your formulation of recommending legal literature. You did legal document recommendation. Legal literature shall refer to educational textbooks in law. Reading your presentation's title, I expect a different word, but still, I think what you did is impressive. Okay, you want to say something about that?
Yeah, of course. I mean, the term literature covers a lot, right? And in our example, we mostly focus on, or only focus on criticisms. So of course, this is kind of a subset of all literature, and I agree. Yeah, would be interesting to expand this to other, yeah, educational textbooks. This might be also something for future work.
Okay. And here we have a comment and a question on, from Trevor Benchcapel. These results all look pretty poor with less than 0.6 for precision and very low recall. Are these techniques useful at all? Even the best is not good.
Yeah, that's actually the generally low scores due to the silver standards that we used. I mentioned that this is the reason why we refer to them as silver standards, not as gold standard, but because we expected that many actually relevant recommendations will be missed by our ground truth, by the silver standards. And this is also what we found in the kind of expert study, where we had one domain expert judging the recommendations. And there we also found that, yeah, relevant recommendations were missed, right? Where the domain expert said, okay, this would be relevant for me, but it was not part of the silver standard. And this is how kind of I would explain the low results. And kind of this is of course one weakness from the silver standard, but I see kind of the big advantage opposed to maybe a user study that is typically conducted, is that we have a much bigger quantity of actually recommendation pairs that we can compare. And this is also what we did in the paper. It's not really now presented in the slides, but kind of we also checked how the actual performance is changing when depending on document characteristics like the document length or citation count, which I would say to do something like this, you need, I don't know, a bigger evaluation corpus, which usually like a user study wouldn't provide. And, so this is kind of the, yeah, on one hand, like one weakness of our silver standard, but also one strength, right? That we, it's difficult, yeah, you have the low results, but on the other hand, you can perform more analysis on the data because you have more quantity.
Right. And we have a question here from Winkles. Perhaps users might find recommendation useful nevertheless. Right.
Yeah, so maybe just as an outlook, so kind of what we did here was really just evaluating a lot of existing methods to have already kind of a limited subset of methods that we now in the next step want to evaluate in an actual live system, right? you probably can't really run like A/B testing on those 40 methods or something that we tested. So at first, we want to select a subset and then now compare the most promising methods in a more detailed study with real users.
I have a comment from Adam Weiner. I agree with Red Bull. It's very useful and important to have studies like this that reproduce, evaluate, and compare results. Okay. You want to say something?
Yeah, thanks. I agree. So that's kind of
okay.
the motivation behind it. That yeah, we found many existing work use user studies, but it's kind of difficult to reproduce, and that's why we thought to have these kind of openly available data sets, and now we can kind of continue working with these data sets, and also then go and actually improve the methods for these data sets.
All right, and I have a question from Dennis Almiller. Did you investigate how the results change with large K? Given the relatively close results, do they exhibit similar performance for more recommendations?
Actually, with larger K, the scores increase slightly. But of course, as you get to a very large K, where they stop to kind of decline again. But yeah, as I mentioned, kind of this setting K to 5 was mainly chosen because kind of the service where we want to deploy this recommender system has kind of this restriction of just showing the top 5 recommendations in the user interface, and this was kind of the reason why we then in the end decided to just stick to this one K value.
Okay. So we have.
But yeah, sorry, kind of the second question was right if the actually relative results changed, but no. So kind of the ranking among the methods, especially among the top methods, it didn't change.
Okay. And so we have just 3 minutes left. If you want to make some final remarks, make yourself comfortable.
Yeah, maybe, yes. Actually, if there is somebody who also runs like a recommender system in a production environment and wants to actually test kind of all the methods, and I don't know, A/B test or something, of course, we are always looking for kind of partners who have access to such a system to run these experiments with real users. So yeah, I'm happy if there's somebody and yeah, who would be interested in doing such an experiment together with us.
So Malte, thank you very much for the talk. And so from now on, we have to move on to the next presentation with Dennis Almiller. And I'd like to introduce him to all of you. He is going to present the third paper of this panel with the title Structural Text Segmentation of Legal Documents. Mr. Dennis Almiller, you have 20 minutes of speech. Afterwards, we move on to the questions. The stage is yours.
All right, thank you so much. I hope everyone can see the screen. And with that, I'm going to start with our full paper presentation titled Structural Text Segmentation for Legal Documents. So this is an equal contribution work between myself and my colleague Satya Almasian. And we have further collaborators Sebastian Lackner and Michael Gertz, also from the Database Systems Research Group in Heidelberg University. So to start with a brief motivation, what is structural text segmentation and especially given legal documents all about? So what we usually deal with in especially legal domain, we have plenty of unstructured document formats, for example, PDF documents. On the right, you can see one example of an end user's license agreement. And so if we look at this document, we can already see that it provides us with a natural segmentation of the context, right? So we have these paragraphs and then even like the headings with a different numbering provide some overview of how we as a reader should interpret this document. However, this kind of structure usually gets lost when we're dealing with a machine readable format. And even when we try to apply segmentation methods afterwards, usually such a paragraph or a document structure is lost. And why is this important? Well, especially for the segmentations, we have a lot of tasks nowadays, for example, in the workshop at this conference, where you're dealing with paragraph retrieval. So having like structured and thematically similar paragraphs is essential. You also have use cases for mergers and acquisitions, or last but not least, document search in general for just cases at like courts, meaning that once we can make sure that a segmentation of a document is still improved in a machine readable format, we're going to have a much better downstream performance, hopefully. And to illustrate this even more is, even if we have some completely nonsensical text like a lorem ipsum example here, we're still going to interpret this as a semantically coherent unit, which is very important for our actual work here, because what we're now doing, and specifically comparing to previous work, is instead of focusing on a segmentation that bases itself just on a sentence level, this has some major problems. Specifically, there is a very narrow context given just by using a single sentence as a boundary. And the other question is, if we already have these thematical units like a paragraph, is it even useful if we split at a lower level, meaning the sentence level, than the paragraph level? And when we looked first into this, specifically for the legal domain, there is a lot of hurdles that come with using existing methods. If you're looking at learning-based approaches, they usually come with custom architectures, which have like restrictive transfer learning capabilities. Most of them are some kind of hierarchical LSTM model, which is very difficult and unstable to train. You have exploding and vanishing gradients. And last but not least, they usually require large amounts of training data, which is not available in domain-specific applications such as the legal domain. And I think actually one of the major limitations that we encountered was not just using tools, but finding some of them. So they are really hard to come by. They either have no documentation at all, they are outdated. We had like one of the repositories that we tried to use that had only 20-year-old C code, no updated version was existing out there. And that was the most common scenario actually, we weren't able to find any code at all. So even if I wanted to apply this to a legal document, I would not have any working solution at the moment. And so this is where our work comes in with its core ideas. And so we have these three main areas that we're going to focus on. So the first one is relatively trivial in understanding what is happening here. We're simply moving the attention span of our segmentation model from a sentence level to a paragraph level. This gives us a much more natural transfer of what elements are existing in the text already. And they kind of serve as a natural boundary that we assume in our work. Similarly, this also introduces a much broader context window, which can be helpful for methods that rely on this contextual embedding. And last but not least, paragraph structures are also something that we can semi-automatically extract from documents that have some vague annotations, such as XML or HTML. The second step is actually more on the model for the segmentation itself, where we rephrase it from a purely sequential document segmentation, where you have one input sample of an entire document, to a pair of binary classifications, meaning we simply look at two subsequent paragraphs and predict whether those are actually thematically coherent. This makes it much more easy to train. This is more stable and has less problems of an architectural sharing. And it is comparatively cheap in that we can use pre-trained checkpoints to actually use existing models and retrain them to our purposes. Given that we now have a different model formulation, we also rely on a different sample generation. And we actually present two different strategies in this work that make it very efficient to sample from a small number of documents even, and that can generate many more samples than the number of documents that are available. We're going to talk about this in more detail, but first I want to just again reiterate from a theoretical point of view what exactly we mean by structural text segmentation. And so what we assume here as an input is usually some kind of document that has a natural structure in terms of the paragraphs here. And indicated here with the colors, we have first three paragraphs that are topically coherent, and then a fourth paragraph that is covering an entirely different topic. And now basically the task of structural text segmentation is to generate a document. This is already where we have the mentioned problems of long-range dependencies. So the question becomes, is it even relevant for the fourth paragraph what happened in the first paragraph? And to exemplify this, in reality, you will have documents that are spanning several pages. And here really the context loses its meaning beyond just the immediate neighbors. Another downside, again mentioned, was the hierarchical training setup. To deal with the embeddings of single paragraphs and then predict over those paragraph embeddings again, you require usually very convoluted architectures that were used in related work that we try to abstract away here. So this is our rephrasing of the segmentation as a binary prediction problem called same topic prediction. And essentially, we make some form of Markovian assumption. So instead of relying on the entire context for the document, we just say, okay, we are training a classifier to predict whether two adjacent paragraphs are belonging to the same topic. Given our same sample document shown on the previous slide, what now happens is instead of a single forward pass, we're going to do at inference time 3 different predictions where we ask whether the first 2 paragraphs would be of the same topic, where the second and third paragraph are the same, and consequently the third and fourth paragraph are of different topics. So this immediately removes the overhead of the sequential nature that I've previously mentioned. And the other point is, if we look at how those samples are basically laid out, just having the neighboring samples, it becomes relatively trivial to just sample many more pairs of paragraphs from the same document. Again, just to highlight, we can still apply this to the entire document sequentially when we're doing inference later on. Okay, so now to the actual methods used in this work. I'm sure you've heard plenty about transformers this week already. I just wanted to mention why we use this specific architecture here. And there's a few points that we thought made sense from our standpoint. Firstly, those come as large and pre-trained architectures, meaning that we do not have to worry about long and expensive training ahead of time. And especially since we can continue from those pre-trained checkpoints, it is much easier to achieve state-of-the-art results. For the fine-tuning as a binary classification task, the architecture basically looks like this, that we feed in 2 separate paragraphs as a single sample, separated by a special token, and will retrieve a class label that is then the prediction of whether those belong to the same paragraph or not. A small implementation detail here, we're actually using Roberta because they have slightly improved performance on all tasks, but we have experimented with BERT as well in this work. Our second methodology is the so-called sentence transformers, which was introduced by Ramis Sengurovic. Specifically, this is a variant of the transformers, which uses the SPI encoder layout. And if you again look to the figure, what happens instead is that we're feeding only one paragraph in a forward pass, and then retrieve these embeddings U and V, and basically predict based on the comparison of those 2 embedding vectors U and V. The main advantage is that SentenceBERT performs extremely well on embeddings and similarity tasks, which is shown in the original paper. And the more important aspect for our work here is that it also effectively doubles the input length. Because remember that for the BERT model, we can only feed 2 paragraphs in one pass. Getting back to the actual sampling of our training instances, we have 2 main strategies here. The first one is called random paragraph. And what we always do is essentially we sample from a reference pair, here denoted in purple, both a positive and negative sample. In the instance of random paragraph sampling, what we do for the positive sample is, or for both actually, we just aggregate all of the red paragraphs into one class and sample a random positive pair from this same topic, meaning that this can also come from another completely different document that has the same topic in it. The negative pair, similarly, will sample from all of the paragraphs across all documents, but from a different topic. And that the problem of this method is that it requires some cross-document normalization, where we basically have to actually normalize here and verify that these sections are actually the same across different documents. The improved strategy that we use is the so-called consecutive paragraph sampling. The name is slightly misleading, but essentially what we do is we restrict ourselves by just sampling from the same document 1 in this instance, where both positive and negative pairs have to come from within the same document, but however, still from either the same section or a different section. The main advantage is, again, that we now no longer require any cross-document normalization, which makes the annotation process for our initial training setup much, much easier. However, there is this one remaining question that we also want to answer in the experiments, that is whether it generalizes well to unseen topics, because now we do not have any relevance between the documents, which might lead to a much poorer generalization. Talking about the dataset that we used in this experiment, we actually obtained a new terms of service dataset from website terms of services. So the main point being that terms of services always have to be available from the landing pages directly, making them relatively easy to extract. And the other benefit is that while they focus on a legal context, they have relatively similar structures and topics across many different documents. So we will obtain, for example, shown on the right, around 20,000 of the documents that have a limitation of liability clause in there. And similarly, we normalize all the other sections as well. This is only an excerpt of the most frequently appearing one. But there is many more because we extracted overall around 40,000 documents based on this Alexa top 1 million list of English websites, from which we then automatically extracted the hierarchical information that was available in their terms of services, which includes linking different paragraphs to a specific section. The one manual annotation that we had to do for our random paragraph sampling is the mentioned cross-document normalization. Specifically, limitation of liability usually was spelled in 3 or 4 different ways. You had limitations of liability or liability just as a single word, referring to similar topics that were manually grouped together. And after all the pre-processing, we're left with around 40,000 usable documents, depending on which task specifically we're looking at. The average length being around 22 to 23 paragraphs and around 3 sections. Now actually moving on to the experiments. So the evaluation that we did was firstly verifying that our binary classification actually works well, and then transferring this into an actual downstream segmentation task. The setup that you're seeing here are the basic methods that we compare for both the classification and segmentation. We will introduce further related work in the actual segmentation task. But for now, baselines that we used are simply averaging glove embeddings. In the previous presentation by Malte, we've seen that this usually leads to really good performance out of the box. Similarly, bag of words and TF-IDF vectors are a good approximation and turn out to be actually competitive with related work. But what we specifically are interested in is fine-tuning transformer models, where we choose a Roberta base model with a classification head, so the so-called ROCLS model, and then a sentence transformer variant of the same Roberta-based model called STRO. As a brief side note to the hyperparameters, we usually sample 3 positive and negative pairs from this per paragraph in the document. And we run all models from 5 different random seeds to account for any statistical variance in the training procedures. Training is performed over 2 epochs for the transform models, and generally our 80-10-10 split is consistent for training, development, and testing. Now, looking actually at the same topic prediction task performance, we compare both the different models and the different sampling strategies. One slight caveat to this is because we sample differently both for the validation and test sets, we cannot compare models between random paragraph and consecutive paragraph sampling here. However, we will still be able to compare those on the next slide when it comes to downstream performance. What we will look instead is how these models perform across like the board, meaning basically we can still look at how glove averaging performs in comparison to the, for example, sentence transformer models. And we see that the sentence transformer models for both strategies perform extremely well, much better than any baseline, and specifically show a better performance, although only slightly better for consecutive paragraph sampling compared to the standard transformer models. Generally, what I want to highlight is also that random paragraph sampling seems to have some inconsistencies in the training stability, which can be due to a variety of reasons. However, we noted a large variance in the performance that was actually subpar to some of the baseline methods. Going on to the actual segmentation and then circling back to the tasks that we actually wanted to solve here. We have this traditional segmentation metric called the boundary error rate PK, which is frequently used in other segmentation works. It gives essentially a probability of 2 samples being incorrectly labeled when compared across the document. And this means the lower the error rate, the better the method is. Furthermore, we introduced 2 related works for which we could find working solutions. One of them is GraphSeg, an unsupervised method introduced by Glavash et al. That is usually also working on sentences. And similarly, Wikiseg, Koshorek et al.'s supervised segmentation model that was trained originally on Wikipedia data, for which we do a training from scratch to have no advantageous embeddings. What we can still see here, and which is consistent with our expectations, is that the consecutive paragraph sampling for every method performs significantly better than the random paragraph sampling. So specifically for the transformer-based method with this classification head, we see that the consecutive paragraph sampling is indeed more stable on the downstream performance as well, and almost competitive with the sentence transformer model from the both from the random paragraph sampling and consecutive paragraph sampling. Similarly, all of the transformer models, with the exception of the unstable Roberta CLS model, outperform the baselines as well as the related work. We do denote that while it seems that those results are extremely bad, this might be mainly due to the fact that they were originally designed to work with sentence inputs and not paragraphs, which is especially detrimental for the unsupervised method GraphSec. However, for Wikisec, we assume that there was also some implementation detail that we might have gotten wrong, leading us to the conclusion that those models would not have been usable by somebody trying to get segmentation on legal documents. Because we personally found this method to be rather hard to understand, what we also did is come up with an alternative evaluation metric for the segmentation, specifically on paragraphs, which is the so-called accuracy up to K. It's rather simple to explain. Essentially, we account for the fraction of documents that have less than or K mistakes. So this actually gives some relevance to our error rate seen on the previous page, because even though we tend to have rather low PK values, if we tend to look at the transformer models, which is this upper curve, even those have only around a quarter of the documents that were classified entirely correctly. Keep in mind, again, those are around 23 predictions that we have to do per document. However, if we account for only 2 mistakes, we can see that already 2/3 of the documents are classified correctly, which might make this still an acceptable segmentation for many downstream applications. But more importantly, it allows us also to give a generally more interpretable result, because even here we can see that the best performing baseline method, the average glove with consecutive paragraph training, is still significantly worse than the transformer models that we see here, with the one exception again being the very unstable Roberta CLS random paragraph sampling model that performs even worse than that. Just as a reference, before anyone would ask the question, we also just tried predicting what would happen if we just said, okay, all paragraphs belong to the same topic, which is the last red curve here, which is predicting simply just always the same topic. Yeah, and with that, we're coming to a conclusion of this presentation. So in summary, the main points that we introduced in this work is a simple but effective training strategy for document segmentation, specifically on paragraphs. We supply a new resource available to the community of web terms of service documents, and have shown in experiments that our proposed transformer binary classification models also translate extremely well to downstream performance tasks. As a brief outlook, what we can do in future work is essentially investigating the actual retrieval performance, specifically in long legal documents. So I've already mentioned in the introduction some of the use cases that might be applicable here. We're also working right now on a more general text segmentation model, which is trained on Wikipedia data, just to see how that compares, maybe also in a zero-shot setting with domain-specific data. And largely, we've already heard about other transformer models that have a longer input context, which might be beneficial for our training on paragraphs. So this is one of the options that we can pursue here as well. With that, here is a link to both our code and data, and as promised, you can easily use this model through the Hugging Face library. Feel free to check it out and give us feedback on our work. And with that, I thank you for your attention, and I'm happy to answer any questions that you have.
Thank you, Dennis. And now we have a question from the audience, from Sabina Wennert. Very interesting talk. I heard you had the data in a HTML format. Do you consider using any superficial cues, font size, boldface from the HTML in the addition to the text paragraph information?
That's a really good question. So what we specifically looked at, why we specifically didn't look at it, is mainly because we use some of this information in the extraction of the hierarchy. So to determine the order between different HTML documents, it's not as straightforward as it might sound. Some of them use the H1, H2, H3 tags, which is relatively easy to extract headings. However, bold-facing was sometimes used as a replacement, or similarly the font size. So we use this in the extraction process, but we actually do not consider this for the segmentation here. The other reason for that is also because we want this to be applicable to not only websites, but also more specifically to any form of document that might not have a similar normalization. So I have worked a lot with PDF documents and can confidently say that even though you might have a larger font size, due to a different font, it might actually appear smaller. So this does not necessarily correlate to the actual interpretation from a human perspective here.
Okay, and you have another question. You make a reference to Wikipedia in the article, which studies terms of service. Both examples are sorts of texts that summarize information, organize them in a stiff recipe. Such texts follow consistently a pattern of structure very different from, for example, Superior Court judges' rules. Are not those findings in structures limited to a more simple chaining of argument? Would it help too with understanding more complex structure?
I mentioned one of the main reasons why we use the terms of service documents is because we can confidently obtain a large number of documents, which is originally required to train our models here. I agree with you that those tend to follow a similar structure. And the problem is mainly that we do not have access to a large enough like supervised / annotated data set with complex cases. I would be very interested in this, and this kind of relates to the future work that we plan to do, where we evaluate an actual retrieval setting, or I'd say like downstream performance of our segmentation models. So yeah, I agree, but this is basically one of the limitations that our work currently has.
Let me see if I have further questions.
Maybe in the meantime, I can also add to this from a perspective of the related work that has done the training on the Wikipedia data, the Wikiseg model. In their own paper, they actually evaluate both within Wikipedia, but also have external training sets that are not necessarily more difficult, but certainly from a different domain. And even there, they tend to beat related work, or at least be on par in performance. So this gives us some hope that our model actually translates well to more complex cases as well.
Okay. All right. So we have a few minutes left. If you want to say a few more words, and Dennis, make yourself comfortable.
Yeah. So again, thanks for your attention. And I think the main issue that we're still looking for is a suitable downstream application where the segmentation can help directly. So if you do know of any shared tasks, or specifically have your own collection of documents that would benefit from such a segmentation, feel free to reach out. And with that, I think that's it from my side. So thanks again for the opportunity to present here. Thank you,
Dennis. And in name of ICAO organization, I'd like to thank all the speakers of the first panel. And now we have a short break, and we'll be back at 11 o'clock GMT for the second panel. Those who want to meet other participants and exchange experience can access the Gather Town platform for a networking moment. The link is at the Open5 platform. Thank you very much, and have a nice day, everybody.
Greetings, everyone. Welcome to the 18th International Conference on Artificial Intelligence and Law. My name is Fernanda Suriani, and this is the second panel of the fourth day of the event. I'm very glad to be here with you. Before starting the panel, in the name of ICAO organization, I'd like to thank our platinum sponsors, JUS Brazil and Albert Einstein Israeli Hospital, our gold sponsors, Logarithm, Legal Code and PG Lawyers, and our silver sponsors, Urbano Vitalino Lawyers, Opsi Bloom Lawyers, and Oasis Open. Now, I would like to introduce Mr. George Borges, who will present the full paper with the title, AI Systems and Product Liability. Mr. Borges, you have 20 minutes of speech. Afterwards, we will move to the questions, and the stage is yours. Welcome.
Thank you very much, and good morning or good afternoon, everybody, depending on which part of the globe you are. AI systems and product liability. Did I share my screen? Not yet, I guess. I prepared some slides, which are hopefully visible now. And it's my subject, AI systems and product liability. Just let me move on, just to make it clear, I'm professor of law. I'm not technician, I'm lawyer, and this presentation is on legal aspects of AI systems. So I'm not going into detail of technical aspects. It's about the law regulating the technology in this case. What is the role of liability within the legal framework for AI systems? Let me briefly introduce. AI systems give rise to enormous expectations. We think that the world will be brighter and richer once we are establishing a framework, a coexistence of humans and AI systems in some future. However, at the same moment, there are some risks associated with AI systems. And the most striking example, which made it clear to the world, maybe was the Uber car accident 2 years ago, when a self-driving car was running over and killing a pedestrian. I'm sure you're aware of that. Another aspect of risks associated with AI systems are machine-made decisions, which is often linked to the questions of algorithmic fairness or machine bias. In this case, very often a machine is making a decision which has an effect on humans. For this presentations, I will not deal with the second group. I will deal exclusively with the risk associated to physical harm and damage caused by AI systems, such as machines like self-driving cars and others. AI systems pose a very specific challenge to the legal systems, as AI system can show what I would like to refer to as behavior. Of course, any machine can function, but what is different between function and behavior? Just as a working definition, I would define behavior in this meaning as the ability to choosing actions depending on a perceived situation, which a traditional steam machine 200 years ago could not do, but a self-driving car would have to do at any moment while it's functioning. This is a challenge to the laws, as behavior or choosing action is an ability which was attributed to humans only, not to machines. And the legal system is not prepared to a machine showing its own behavior. It's not surprising that liability is in the core of the legal discussion for an adequate legal framework for AI, at least in Europe. From 2018, the European Commission was active in this field, starting, for instance, with the communication of 2018 AI for Europe, where a good deal of the paper was dedicated, surprisingly, to questions of law, in particular liability. The next, as a step, I want to refer to the work of an expert group on liability and new technologies, which was established by the European Commission in 2018 and delivered its final report in December 2019. I will refer to this as the expert group made the conclusion that some amendments of the current legal framework are needed, in particular, the introduction of new rules on liability. The European Parliament took the opportunity in October 2020 and suggested the introduction of a civil liability regime for AI systems, in particular, including a proposal for regulation on liability of operators of AI systems. And most recently, the European Commission in April 2021 published its proposal for the so-called AI Act. The AI Act is a very, as it's demonstrated by its title, a suggestion which introduces fundamental principles for the use of AI systems. By substance, however, it mainly restricts to the introduction of the duty to establish a risk management systems by operators and producers of AI systems. It does not refer to any liability rules, since these rules will be dedicated to a specific insurance for liability for AI systems. We expect the first proposal by the European Commission to be published in fall this year or spring next year. I want to talk about liability in AI systems. So what are the functions and concepts of liability? This is very important to bear in mind when we talk about the detailed questions. The traditional function of civil liability is to offer compensation for damage occurred. However, a second and possibly even more important function of civil liability is that it creates incentive to the addressee of liability to adapt his behavior, for instance, driving carefully in order not to be liable. When we talk about concepts of liability regimes, we should distinguish between the traditional fault-based liability, which is known worldwide in every jurisdiction which I'm aware of, where liability depends of the existence of a breach of a duty of care. You're only liable under fault-based liability if you breach a duty of care. As a contrasting concept is well known, the concept of strict liability, which exists in a huge number of variations. Basically, the idea of strict liability is that the addressee of liability is obliged to pay damages whenever a damage occurred within a defined sphere of risk. Just to give an example, under many jurisdictions, the operator of a car will be liable to pay damages whenever an accident occurred while operating the car. This is a very easy example of strict liability. The sphere of risk is the operation of the car. And these rules are very important for AI systems as well. The last aspect of the conceptual framework of liability certainly is to whom the liability is addressed. In the current discussion, there seems to be a trend on introducing new rules on strict liability of the operator of an AI system. So the basic idea is that the person being obliged to compensate for damages should be the operator of an AI system. Regarding the producer of the AI system, many authors and legislators refer to the existing framework of product liability. And that's why product liability is so interesting for our questions, since this is, at this moment at least, dedicated as serving also to or dealing with the challenges posed by AI systems. The legal framework of product liability is different, obviously, in all jurisdictions. In in particular, US law played a very important role in the development of product liability rules. However, in my presentation, as I'm European and in particular German lawyer, I would like to refer to the system of the European product liability, which is applicable all in the European Union and is similarly known by the basic concepts in many other jurisdictions worldwide. The basic rule of the product liability directive is set forth in this Article 1. The producer shall be liable for damage caused by a defect in his product. So there's liability for any damage caused by the product if and only if the product is defective. So the defect of a product is the main reason or source of liability. Please keep this in mind. I will come back to this in a minute. Now, the question is, how can we apply product liability directive to AI systems? It goes without saying, and is not disputed at all, that cyber physical systems, which is a functional unit of hardware and software like self-driving cars, robots, and so ever, are products within the meaning of the product liability directive. It is still somehow disputed, or there's still some uncertainty as to the question in how far software which you can download from the internet can be considered as a product within the product liability directive. Most authors nowadays consider software being a product, and we expect an amendment of the product liability directive, which is announced for next year, which will probably expressly include software into the regime of product liability. This is an important step, as for the past 30 or 40 years, many people were thinking product is never error-free, so software should not be subject to strict liability, but that is state of, or will be probably be state of the art within a few years from now on. When it comes to AI systems and in particular systems which use machine learning to develop their function, the question arises in how far a neural network, or let's say the functional unit of a neural network and the software to run it, can be considered as a product. But obviously, if software is a product, also the functional unit of software and the data model has to be considered as a product. For this reason, all kind of AI systems which are in place will be subject to product liability under the European scheme. The next question is, who is the producer? Who is the addressee of liability? And this is the producer of the AI system according to Article 3 of the PLD, as we call it. The producer is addressee of liability is the producer of the finished product, but also the producer of any raw material or of a component. So if software is a product, in most cases a component, this programmer of such software will be producer and can be liable under the PLD. In the case of a neural network, which gathers its abilities or functions by training, as we know, the person who is conducting that training has to be considered as a producer for the simple reason that the neural network only acquires its functions or abilities via the training, and the training process which is initiated or steered or conducted by a person, that has to be the producer. To sum up, we don't have any difficulty in applying the PLD on AI systems, including systems which are based on machine learning, and we don't have any difficulty to make liable any person who is responsible for the functionality of such system or software. Now I would come turn to the most difficult question, in my view, with regard to AI systems and product liability. As I said in the first part of my presentations, AI systems have the characteristic that they can show what I would like to call conduct or behavior. In this way, they're different from traditional products. A defect is defined as an insufficient property of a system. So we have to refer to the properties of the system and check if they are fulfilling the expectations or not. Insofar they are below the reasonable safety expectations, the product is to be considered as defective. So in the case, however, how can we apply that systems to an AI systems? Again, the self-driving car offers a simple example. If a self-driving car is running flawless for 1 million of kilometers or even miles, is it defective if it causes an accident in the 1 millionth and first mile? This example makes it clear, in my view, that conduct or behavior of a system is not per se a property of the system. We should and have to distinguish between property and conduct. However, a kind of bridge between conduct and property can be established if we assume that the ability to behave in a certain way in a given situation can be considered as a property of the AI system. So the property, which is the reference point for defectiveness, is the ability of the system to behave in a certain way.
5 more minutes, Mr. Portes.
Excuse me?
5 more minutes.
That's exactly what I expected. Thank you so much. So product, just to make it short, is not a liability for faulty behavior. And this is important since we have to establish this ability. The next question, and in my view, most difficult question, is what is the reference point for the conduct? If you refer to the ability to conduct or behave in a certain way, what is the reference? Is it human behavior? So far, the legal framework doesn't offer any answer to this, since the legal rules were designed for humans, not for machines. Certainly, human capability can serve as a first orientation for safety expectations to AI systems. You should certainly expect that a self-driving car would behave similarly than a human driver, for example, would respect traffic signals or so. However, obviously, there's no limitation by the expectations are not limited by the reference of human capabilities. You definitely can expect a self-driving car to use the brakes much faster with a faster reaction than a human driver. It makes it clear that we need a kind of independent expectations for machine, which are designed to the capabilities of machines and not just apply the rules which have been designed for humans. And the next question is, what is the accuracy? In this conference, as in general, when we develop AI systems, we are proud of accuracy of our tools. But what is the accuracy which we have to expect from an AI system? Can we expect an error-free AI system? Can we expect that it will always, in any future situation, behave correctly? Is that the test? Is it 100% error-freeness what we have to demand? Certainly not, as this would be a liability for behavior, not for an ability. That makes it clear that we have to find out what the fault tolerance in case of an AI systems is, and it's obvious that this depends very much on the risks associated with such systems. You would probably expect a higher accuracy from an airplane or self-driving car than from an AI system which is supporting a lawyer in searching decisions or arguments. And the next question, the next challenge then is, how can we assess that the system fulfills the safety equations, the error, the required accuracy? And this goes via testing. That's why testing of AI systems play a major role in the concepts of liability for AI systems in the future. Proper testing can also be a safety expectation of the product itself under the PLD already. So even if you apply the common, the present legal system, testing can be part of it. The last point I want to mention is the most important one in practice very often, that's the burden of proof. Under the PLD, the injured person shall be required to prove the damage, the defect, and the causal relationship. So the burden of proof is on the victim. Under most legal systems in Europe, we don't have any tools to support the victim in collecting the facts. And even if we had some kind of pre-trial discovery, it is very difficult to establish the fact. For this reason, the expert group, which I mentioned earlier, is suggesting the shift of a burden of proof and say in certain situations. The expert group did not clarify under which circumstances such shift of a burden of proof should be in place. So the crucial question then is, what are the conditions for such reversal of the burden of proof? I would like to suggest a solution which I described in my paper, which is that the reversal of the burden of proof for defectiveness of a product should be in place in the case of faulty behavior of such product. So once we can establish that the AI system behaved in a given situation in a wrong way, the reversal of the burden of proof that the product as such is not defective shall be on the producer. To conclude, product liability can in general be applied to AI systems. One of the main challenges is what is to distinguish between conduct or behavior on the one side and a property of the system on the other side. However, we can bridge this by considering the ability to behave in a certain way as a property. There are two main challenges in my view. The one is the definition of the expectations regarding the accuracy of an AI system to behave properly. And the other one is the proof of a defect, the burden of proof of a defect. And here I would like to suggest to introduce a shift of the burden of proof for defectiveness in the case of faulty behavior. And that's it. Thank you very much for your attention.
Thank you, Mr. Borges. It was very interesting. Actually, there are many concepts of law that are being challenged by AI, and this is definitely one of them. We have a question from Mr. Adam Weiner. Actually, he's asking you to comment about the development of these issues in the UK and USA, if possible.
I'm not familiar with the recent developments in the US. In the case of UK, which was part of the European Union until very recently. So in the past, it has had the same rules. And of course, the PLD is still current legislation in the UK. So all I said for the current situation refers to the UK as well.
Okay. Another question from Marcelo Lopes is, if product liability law can be applied to situations involving discrimination or otherwise unfair assessments by AI systems, what could be done to encourage producers to avoid biases in their systems?
Thank you very much for that question, which refers to my next presentation. It's a very interesting one. To cut it short, in my view, testing is the answer also to fight against bias and discrimination, since the big advantage of AI systems compared to humans is that we can reproduce their choices. So they are open to testing, even though there are limits to testing. Just to give an example, it's hard to reproduce the Uber accident, since there's so many factors and so many potential data which you can never really re-establish. Also, if you consider that an AI system would assess a person based on a video interview, the amount of data makes it very, very hard to do just exactly the same. So even though there are limits, testing is the very big advantage which we have when it comes to machine-made decisions compared to human-made decisions.
Okay, good. Francesco Sovrano is asking, what if it's not possible to assess a defect nor a lack of defect?
What if it's not possible to assess a defect?
Nor a lack of defect.
If you don't know if it's defective or not, in that case, there is no claim for damages. So the victim has to establish the existence of a fact, and if the facts do not allow the judge to assess that there was a defect, the case will be dismissed.
Okay, and can you have some comments about the Teubner ideas of you give a personality, legal personality for AI systems for liability issues?
Thank you very much for that far-reaching questions. As we know, the idea of a legal personality, which was brought up by the EU Parliament in 2016 and discussed worldwide after that, has not found many friends in most Western countries. In Europe, it was Estonia who showed a sympathy and announced some legal action, but later refrained from it. And most scholars in Europe strictly oppose the idea of legal personality of AI systems. Surprisingly, in other areas of the world, there is more openness to this. When I have a frequent exchange with Japanese colleagues, and interestingly, the colleagues in Japan were much more open to the idea of giving personality to AI systems than their European counterparts. So it is very interesting to see that even though intuitively a European lawyer would certainly reject the idea of attributing legal personality to machines, like I would do actually, we have to consider to see that the idea is not, it's not impossible to conceive legal personality. Certainly what we will need is an idea of addressing machines in their behavior. I hope I could make it clear in my presentation that conduct is not a property and that we have to deal with a system, a machine, which is behaving similar to, in its own way, but similar to a human who is also choosing his action in a given situation. And that point is just not addressed by the current legal system. And if that is an idea which you can take away from my presentation, I would be very happy.
Yeah, actually, it's a very, very interesting point of view. I really like it. Thank you very much, Mr. Borges. Now, I will introduce you. Sorry, do you have any more comments to finish? Any?
No, thank you. That was my closing remark already. Thank you very much. Thank
you very much. So next, I will present you to Francesco Sovrano, who will present a short paper called A Dataset for Evaluating Legal Question Answering in Private International Law. Francesco, please, the stage is yours. Welcome.
Thank you. Thank you very much. Do you see the slides?
Yes, we can see.
Okay, that's great. And so, okay, I'm going to present this paper of ours that's a data set for evaluating legal question answering on private international law. And okay, so why private international law, first of all? And that's the first question I'm trying to answer. The answer is that this is a complex legal domain, as you are aware of, and that presents frequent conflicting norms between a lot of legal sources, a hierarchy of legal sources, legal domains, adopted procedures, and so on and so forth. So it's quite complex to be able to somehow handle all these different information, all this information. And so legal experts in this case have to access heterogeneous sources to apply hermeneutics, and also they have to possess a deep understanding of legal language. And at least this is clear to me, not being a legal expert at all. I'm more computer science. So when I try to read some kind of legal source, I always struggle to sometimes disambiguate the meanings from natural language to legal language in a sense. Anyway, so hermeneutics is still an important aspect to be aware of when analyzing these legal sources. And so reasoning over private international law is quite challenging, especially if it's automated reasoning, and especially when regulations change frequently or are big enough in size. And so even for a human can be daunting in some cases because of the differences, the subtle but clear and strong differences between jurisdictions and the sources. And so here we go to our research question. So the idea is that we identify this being a challenging aspect to tackle, a challenging problem for artificial intelligence. We are interested in providing automated answers to questions written by legal experts for extracting information out of private international law legislative texts. And so this is kind of challenging according to state of the art, at least. And so the first point is to be able to evaluate such a tool, any kind of tool for automated answering to these questions. And properly evaluating requires the identification of a data set, an evaluation data set. And this was the very first, let's say, step we had to take in order to consider, in order to develop any kind of automated question answering tool. And so this is why we are focusing today with this paper. We are focusing on this kind of on a data set, and because it's mandatory for any kind of tool for the evaluation, proper evaluation. So we improved over our previous work using a larger and more curated data set on private international law, and we published that work on Jurex 2020. And we decided to extract the data set out of the 3 regulations European Union from the European Union, and these are Rome 1 regulation that's on the law applicable to contractual obligations, Rome 2 regulation that's on the law applicable to non-contractual obligations, and Brussels 1 bis on jurisdiction and the recognition and enforcement of judgments in civil and commercial matters. So
4 minutes, please.
Sure. So the target of our tool is the practicing lawyers with reasonable yet not expert knowledge of private international law. And so the dataset is clearly going to be a set of questions and answers, and expected answers for that questions. And these expected answers are in the form of articles, recitals, or commission statements, if any. In this case, we decided to consider recitals beside articles because the user persona could be interested in prima facie interpretative tools. And so we followed a methodology for building the dataset. So we asked to 5 legal experts to be involved in this. And so 2 of them selected the questions, trying to not be speculative or trying to be agnostic to elements that are placed outside the regulations. While other two independent experts try to find a set of expected answers using only the information within the regulations. And they had to avoid interaction with each other. And after this process, we had to merge the answers given by the two legal experts because there were subtle divergences between them. And so we used a third legal expert to do that, disposing of a higher level of expertise. And so furthermore, we also classify the questions according to a heuristic we called context specificity. And so we labeled questions as highly specific when the answers were exactly in the domain of the regulations. And normally when they were falling just in part within the scope. And otherwise, low specificity was given to the question. After the process, we had 17 questions, and of them, particularly 1/3 of them had a low specificity, 1/3 a normal specificity, and 1/3 a high specificity. And we also try to evaluate the data set in a sense using a tool. So we try to understand the behavior of existing tools on the new data set. And so we took the one from our previous experiments, the one mentioned before from Juris 2020. And the expectations were that the QA tool, the question answering tool, was likely to not perform well on questions with low specificity because supposedly they require multi-hop reasoning, and that tool was not equipped with that capabilities. And so this is a screenshot of the tool. So you see the question and the answers. After the evaluation process, we got the scores, and we grouped them by questions specificity. And we observed that the expectations were somehow met because we saw that the F1 scores increased proportionally to the context specificity. And that's quite reasonable because the specificity of the question is low when it asks something that is not closely related to the regulations. Multi-hop reasoning is usually required to answer questions with low specificity, but the baseline was not equipped for that, as we said. And so, as an example, this question, how should a contract be interpreted according to this regulation? This has a very low specificity, because it probably requires to pinpoint both recitals and articles for a proper answer, and so therefore more distinct and distant paragraphs, and so requiring multi-hops in the regulations, in the knowledge graph at least, the underlying the regulation. And so our belief is that most of the speculative questions would require broader view on the subject matter, having a low specificity to the regulations, therefore requiring multi-hop reasoning. So this paper, this dataset should help us in the future to evaluate properly new algorithms, to understand whether they're failing to different tasks, because question answering is probably involving different tasks. It involves answering to questions with a low or medium or high specificity. And being able to disentangle them could be beneficial for evaluation. And so we extended our previous work presented during Juris 2020, proposing this larger and more curated data set for the evaluation of private international law, of questions on private international law. And that's it. So I think I finished. Thank you for your attention.
Thank you very much, Mr. Francesco Sovrano. We'll have a question for you. And at the third section of your paper, when you talk about context specificity, you say that multi-hop reasoning is usually required to answer questions with a low specificity, but the baseline is not equipped for that kind of reasoning yet. What are the main challenges to make your model able to answer this type of question?
Oh, no, okay. Yeah, it's quite challenging, especially in this context, if you look at state-of-the-art question answering tools, especially applied to legal knowledge, they always try to handle single or two-hop reasoning questions. And it's very challenging to go farther in a sense. But I believe that one of the process, one of the ways to go could be to integrate this question answering tool that is mainly based on deep language models, to integrate this tool with external reasoning tools. They are designed to handle multi-hop reasoning questions in a sense. So the point here is that we have natural language, and that's quite and that's good for deep language models. And we have formal reasoning tools that are not capable of handling natural language. So the challenge is to be able to, as always in a sense, to bridge the gap between natural language and formal languages. And I believe that with the tool we are providing, we are using as baseline, this is possible by extending the knowledge graph, in a sense, the underlying knowledge graph that is used to answering questions, with new information coming from these reasoning tools. And that could be possible by, I don't know, using some discourse theory or some, by analyzing the language, the structure of the language and the information within the language in a proper way by means of existing theories of language, natural language, such as discourse theory or argumentation theory or so on. So I believe that this could be possible in a sense to, just to approximate some proper, let's say, level of multi-hop reasoning. I don't know, it's open, it's still an open problem for us.
Perfect. Thank you very much, Mr. Francesco. Do you like to address some more final comments?
No, I think unless there is any more questions.
Not yet. Actually, we have a delay, so maybe some more questions will come, but not yet. So thank you very much. And next, I will present you to Mr. Fernando Esteban de la Rosa, who will present a short paper called Making Intelligent Online Dispute Resolution Tools Available to Self-Represented Litigants in the Public Justice System. Mr. Fernando, the stage is yours. Welcome. We can see it. You can go on. You were muted. Okay.
Now,
yes.
Thank you very much. First of all, I would like to thank the organizer for such a great organization of this conference. Thank also for allowing me to present this contribution together with my colleague, John Selesnikov. He's a regular at the association's conferences, not me, in this case, it's my first time. I come from the University of Granada in Spain, where artificial intelligence and law studies are being enhanced through a research unit created in 2018 named Digital Society, Security and Protection of Rights. This is an open research unit aiming to promote joint research initiatives, especially with researchers belonging to this association. This is the name of my our contribution today is Making Intelligent Online Dispute Resolution Tools Available to Self-Represented Litigants in the Public Justice System. Our contribution focuses on the technological changes being made to justice systems to support the vulnerability of self-represented litigants. This situation of the self-represented litigants is becoming more and more frequent and is increasing in both common law and civil law justice systems. The aim of this presentation is first describing the use being made by some jurisdictions of combined ODR and AI tools for self-represented litigants, and second, to promote the debate on the ethical governance of making these tools available to self-represented litigants. To this, we will follow an European approach. The point of departure, is that ODR, online dispute resolution, is moving more and more from ADR to courts. ODR allows users to appear in court on their own without legal assistance. ODR allows the users to file a claim, to follow a case, to negotiate with the other party, to have the intervention of a mediator, and also to have a hearing through video conference, telephone, face-to-face. But it is possible to move a step forward, and some jurisdictions have begun to provide justice users with intelligent user-centric ODR systems incorporating information and assessments AI tools, diagnosis AI tools, and predictions tools. The important thing is that this is in order so that disputants can be better prepared to deal with a direct negotiation conducted online with the aim of enabling the dispute to be resolved without the need for a court ruling. We have some examples stepping forward. Here we have the task platform Respiger, where the parties are informed of rules such as those for dividing property, child support, and standard arrangements for visiting rights, so that they could agree on the basis of informed consent. Also, we have the British Columbia Civil Resolution Tribunal. The CRT is the most significant current widely ODR system that comes closest to providing a full suite of dispute resolution services. It offers the diagnosis of the dispute by providing an expert system decision tree and provides legal information and tools such as customized letter templates. Between 2017 and 2018, China has also created 3 new internet courts in Hangzhou, Beijing, and Guangzhou. These courts only have jurisdiction over internet-related cases. Litigation risk assessment aims to help the party without legal knowledge to identify and exclude common litigation risk, thereby reducing unnecessary losses. Meanwhile, the assessment can make the party aware that litigation is risky and costly and guide the party to choose ADR or diversified dispute resolution. The system can automatically generate a complaint letter by simply selecting the suitable response options. There are also interesting projects in Estonia and Singapore. For instance, Singapore is developing an ambitious online system, initially only for injuries arising from motor vehicle accidents. An outcome simulator will provide guidance to potential claimants prior to the commencement of the proceedings, helping them to decide on offers from insurance companies. The aim is for parties to first use the technology to reach amicable settlements without professional legal advisors. In order to give an answer to the situation of the self-represented litigants, the justice system should be adapted to support them. Some of the facilities refers to the use of AI tools. The system should allow users to enter information, ask them for appropriate data, and provide for templates to initiate the dispute. The system should provide information on how important it is to act in a timely manner and where to send the dispute. But the system should also provide tools for reality testing, books, articles, reports of cases, copies of legislation, and videos, and the most important thing, the possibility of having information about best alternative to a negotiated agreement in order to promote the direct settlement.
5 more minutes, please.
Okay, sure. Communication tools are also important. Decision support tool, if the disputant cannot resolve their conflict, software using game theory or AI can be used to facilitate trade-offs, and drafting software is also important. In Europe, there is a concern about ethical issues and government related to AI. It is well known, the European Ethical Charter on the use of AI in judicial system and their environments. But we have also documents in the field of the European Union, like the opinion of the European Economic and Social Committee, the Digital Revolution in View of Citizens' Needs and Rights, the White Paper of the European Commission on Artificial Intelligence, the resolution of the European Parliament with recommendation to the Commission on a framework for ethical aspects of AI, the communication from the Commission called Digitalization of Justice in the European Union, and finally, the most important document today is the proposal for a regulation laying down harmonized rules on artificial intelligence. The position of the European Ethical Charter is clear. It's admit that there are inherent risks in these technologies. These tools could create a new form of normativity. The report is skeptical about considering this compatible with the individual right ensuring in the European Convention on Human Rights, fair trial, the right to an independent and impartial tribunal. So it's not clear this compatibility. The position of the European Commission is a little bit more open. It's considered also that the proposed requirements in the white paper on increased transparency, human oversight, accuracy, and robustness of the systems aim to facilitate their beneficial use while ensuring that fundamental rights, including non-discrimination, based on sex, racial, ethnic. So it would be possible to respect the due process principles. And the position of the new proposal for regulation is open, but it's not completely clear. So it is make a separation between both possibilities of using AI. But at the end, the decision would be in the hands of the states. We submit that neither the recent official documents of the European Union nor the Ethical Charter on the use of the AI in judicial system and the environment deal directly with the admission of AI tools aimed at enabling the party to assess their legal position. Because self-represented litigants generally lack legal skills, and in view of the objective to encourage negotiation, we submit, John and me, that this issue of technology for this purpose should be considered high risk. However, in view of the beneficial impact of the functioning of the judicial system, it is necessary to identify the technical limits and the safeguards to be met by the machines offered by the public justice systems to self-represented litigants. From this point on, the need arises to find out what information should be provided, which technology should be used, and what safeguards need to be put in place. But this is the topic to another conference. Thank you very much for your attention. And John and me, we will pleased to answer the questions.
Thank you very much, Mr. Fernando Esteban de la Rosa. It's a quite interesting subject. Well, I have some questions for you. And actually, it's taking from your conclusion. So what are your suggestions of safeguards to enable the use of AI by judges and at the same time avoid bias against minorities or the development of rule of law, meaning the evolving interpretation of the law? For instance, the case Brown against Board of Education in US, if it was based on AI, all those best precedents, past cases, maybe it would be an impact to evolve the interpretation of racism in US. So that's the question.
I must say, I'm sorry. Can I say on this? Yeah, I mean, Brown versus Board of Education is something I've written a lot about. It's an incredibly important case because the basic premise was in 1896, the Supreme Court of the United States in Plessy versus Ferguson said segregated schools are okay as long as they're equal. In 1954, in Brown versus the Board of Education, they said, we have observed over the last 58 years that segregated schools are not equal. So we can't allow segregated schools. Now, the basic point coming out is that AI should never, you should not have robots making decisions. And none of us are actually arguing that. It has got to be the human judge that makes the decision, but the AI can help the human judge make much better decisions. The AI can also be transparent. You can look at the way, often judicial decision-making is not transparent. With computer systems, you can look at how they reached a decision, and if you're not happy with the process, you can undo it.
Do you want to answer as well, Fernando? No.
Yeah, only to say that the possible measures in order to control, to submit to control, it depends on the technology used. But because one thing is to develop an expert system that is a question of programming, and other thing is using machine learning. It's completely different. Indeed, it is important to decide which is the technology, the best technology, in order to offer information to the self-represented litigants, because of the different functioning of this technology. So, but for instance, for expert systems, that I probably would say that it is better to use expert systems than technology of machine learning in order to inform users. Maybe it would be possible to use some of the recommended in the white book of the European Commission, like concerning possible testing of application and the need to provide relevant documentation on the purpose and functionalities, maintaining the possibility to correct errors, and providing information to users that the answer given by the machine may not necessarily match the answer that would be given by a judge hearing a case. All of these are causal measures that it could justify the use of this kind of technology.
Okay, another question. You said that the self-represented litigants push the limits of judges' impartiality, and that ODR tools may overcome this issue. In your opinion, the fact that the court provide information, like the British Columbian Tribunal, in such a way that the parties may obtain a prediction of the outcome, even though meant for the preliminary stage of direct negotiations conducted online, can also affect court's impartiality, in the sense that this prediction may cause a machine bias.
Well, I might say nothing is ever unbiased. We all have social, political, cultural values. Now, the whole idea of, you know, self-represented litigants have always been at a disadvantage compared to those people who get good professional advice. So having contacts, having money is always a benefit in any system. What we're saying is that the use of online dispute resolution systems and systems to support litigants in ADR is going to improve their chances. It's not going to make it equal, it's not going to make it perfect, but it will provide opportunities that have not been previously available.
And do you think AI, in a sense, in the system, the justice system, how can we avoid the machine bias? I mean, all the prediction, all the drafts or the propositions made by the system that is thought as more neutral? Can it happen? How we can manage the safeguards? Do you think it's only to use not using in the justice system the learning machines, only expert system? Is there a solution?
It won't be perfect, but there are human biases that that's the whole legal profession, and certainly the legal academic profession. What we're trying to do is to improve it. And the one way to bias is to make everything transparent. And what I'm arguing is that the legal system has generally been a mumbo jumbo, which non-professionals don't understand. Technology, particularly expert systems, rule-based systems, is going to help you understand this process.
Perfect. I totally agree. The user-centric technology using to simplify all the complexities of the justice systems will be a great advantage for the vulnerable ones. Thank you very much. And well, now we'll have a short, do you have any final comments? John, especially because, no, okay. So thank you very much for your participation in iCAIL. And now we'll have a short break for 30 minutes. And those who want to meet other participants and exchange experience can access the GatherTown platform for a networking moment. The link is at the OpenFi platform. Thank you very much and see you soon.
Thank you.
Thank you.